Welcome to Calculus. Today we will investigate finding limits of average rate of change as well as finding limits of difference quotients. And it turns out that they're much the same thing. We'll take a look at 4 examples total, beginning with 2 limits of average rates of change. Let's head over to our notes screen. Our first example here is find the limit as x approaches c of the average rate of change of f from c to x. And then we're given that same word statement in symbols. That is, find the limit as x approaches c of f of x minus f of c over x minus c. And the function we're interested in calculating this limit for is f of x equals 8x cubed. And we're really interested in the x value approaching 2, c equals 2. Well, we'll jump right into that. Before we do so, though, what we need to decide is where did this limit expression come from? So I just want to sketch a small graph here to the right. And let's consider that we've got this function. This is kind of a caricaturized cubic function. And really what we're calculating here is the average rate of change. So just to remind what average rate of change looks like on a graph, it's really about slope. So to think about how we'd calculate slope, I'm just going to locate a point here. Let's call that C. And that's a value on the x-axis. So when I trace over to my y-axis, that's going to be the output f at C. And that'll be an actual number. So for our example, RC is 2. So that would be like 2 f at 2. But let's keep it generalized. So we'll go with C and f at C. Well, to think about how we would calculate the slope at that point, we extend it. So we say, okay, let's imagine another value out there. Let's call that x. And then if I trace up to the graph, that's my point on the graph at x, and trace over the y-axis, that y value is f at x. So if I use just the algebra 1 definition of slope, remember that's rise over run. So it's my 2 y values subtracted over my 2 x values subtracted. And let's say what that would look like as an equation. So for my numerator, I would have f at x minus f at c all over, so that's my rise, all over the difference of x minus c. So it really goes back to an old concept that we've got from algebra 1. Now the part we need to incorporate is the limit. So what's this idea of a limit? Well, let's look at the line that would go between those red and light blue points. So that would be something like this green line. And just looking at that green line, how many times does it intersect our blue function there? Good, twice. So geometrically speaking, this is a secant line. If you remember back to how secant lines intersect a circle in 2 points. So to think about slope, really, I want to minimize the number of intersections with that line with my function. So I want to bring x as close as possible to c so that I'm bringing in this x value. So if you imagine this x value is going to travel along there and changes its slope as it gets closer to my original c. So I can even kind of draw some repetitions here. And the idea is I ultimately want to get down. I'm going to back off a few of these lines. I want to get down to the exact line that goes through that point just once, and that's the tangent line. If I can find the slope of the tangent line, I can claim that that's the slope of the original function, not between 2 points, but at that point exactly. And what gets us there is this idea that it's the limit as x approaches c. As x approaches c. So we're saying that x interval is getting smaller and smaller and smaller, which should give me the instantaneous rate of change. Well, we start with average rate of change. So that's kind of the background behind this limit expression. Let's put it into some nuts and bolts use. Let's calculate the limit. So we'll write here as x approaches, our c value is 2, of our function f of x. So what we'll do is we're going to note from the way that the average rate of change expression is written, you just write f of x to begin. So that for us is 8x cubed. And then I want to calculate f at c. So for us, f at c is going to be 8 times 2 to the power of 3. So I'm actually putting in that c value into the expression. And then down below, x minus, again, c is 2. So that sets it up. At this point, I want to simplify and just evaluate that limit. So I'm going to start in the numerator. Numerator would reduce to 8x cubed. And then 2 cubed is 8. 8 times negative 8 is negative 64. I'll repeat my limit expression. Limit as x approaches 2. All over x minus 2. Now, what I need to do to that numerator is factor it. So I'm going to bring limit as x approaches 2. I'm going to factor out an 8. And that'll leave me with x cubed minus 8. And what we need to remember is our strategy from Algebra 1, Algebra 2, pre-calculus. How do I factor this difference of 2 cubes? Well, we remember how to do that, so let's factor that. So this is the limit as x approaches 2 of 8. And then remember, for difference of 2 cubes, you take the cube root of each term. So cube root of x cubed is just x. Cube root of 8. What's the cube root of 8? What number times itself 3 times is 8? Good, that's 2. So then it's x minus 2, and then the trinomial x squared plus 2x plus 2 squared, which is 4. So again, we're just using that Algebra 2 pre-calculus difference of 2 cubes pattern to factor that x cubed minus 8. When I put x minus 2 in the denominator, what do you notice above and below? What do you notice? Good, I've got a duplication of x minus 2 and it cancels out. Now that's good news for us because that was gonna make this an indeterminate form. It's gonna be divided by 0. If I put my limit value of 2 into that denominator, 2 minus 2 is 0. But we have circumvented that problem because we are now on just one level. The limit as x approaches 2 of 8 times x squared plus 2x plus 4. So now I'm ready to calculate that limit. I'm just going to do direct substitution. 8 times 2 squared plus 2 times 2 plus 4. So I'll evaluate that. 2 squared is 4 plus 2 times 2 is 4 plus 4. So it's 4 plus 4 plus 4. That's 12. So this is 8 times 12. And if we multiply 8 times 12, we're going to get 96. And that is complete. And just to interpret what we've just calculated, the average rate of change as we approach positive 2 on this function 8x cubed is 96. And that's about right. If we think about that function, it's very not like our caricaturized cubic function here. It's very steep. So a slope of 96 is almost vertical. Let's take a look at one more example using this idea of the average rate of change. So here we want to find the limit of x as, the limit as x approaches c of the average rate of change of f from c to x. So we're going to use that same limit as x approaches c of f of x minus f of c over x minus c. What changes here is our two functions. So we got square root of x is our function, and our c value is 1. So let's set up our limit expression as limit as x approaches 1 of f of x is just square root of x minus square root of 1 over x minus 1. So that's the setup. Again, I've completed that part. Now what I want to do is I want to evaluate that limit. So this becomes, we'll do some simplifying in the numerator. Limit as x approaches 1 of the square root of x. Square root of 1 is 1, so that's minus 1 over x minus 1. So if I were to do direct substitution, I'd be putting a 1 in here in the denominator. 1 minus 1, 0. Numerator square root of 1 minus 1 is also 0. So direct substitution would give 0 over 0. That's not what we want. So think for a moment to strategies we've used to calculate limits involving a square root. Excellent. So what we can do at this point is multiply by the conjugate. Remember that strategy from previous lesson? So if you got a square root plus or minus a value, you just multiply by its conjugate. So this would be the square root of x instead of minus plus 1. And we'll do that above and below. And that's valid algebraically because that's got the value of 1. Something divided by itself equals 1. Let's multiply that out. So over here on the left, it equals the limit as x approaches 1. So again, I'm going to FOIL. Remember how that worked is square root of x times square root of x. Outer term square root of x times positive 1, so plus 1 square root of x. Inner terms negative 1 times square root of x. And then last terms, negative 1 times positive 1 is minus 1 over, remember for the denominator, really the part that we don't use to create the conjugate, we just leave it unfoiled. So that's x minus 1 times square root of x plus 1. Let's see how that simplifies at that point. So now it's got the limit as x approaches 1. So square root of x times square root of x is going to be just x. My middle terms cancel out because they're the same, but they have the opposite signs. And then I'm going to bring minus 1, so x minus 1 above. And then I'll just import those two factors from my previous step denominator, so x minus 1 times square root of x plus 1. And I'm going to pause there. What do you notice above and below? Good. Same type thing we saw in the previous limit. I've got the identical binomial above and below, that cancels. And really that takes away the part in our limit expression that was forming that indeterminate form, that 0 over 0, it's gone now. So what we've got is 1 over square root of x plus 1. And so we're ready for direct substitution. I'm going to drop the limit, put 1 over the square root. X was approaching 1 plus 1. So square root of 1 is 1, so that's 1 over 1 plus 1, which is 1/2. And that completes our expression there, our calculating our limit as x approaches 1. Thank you for joining these first two examples of calculating average rate of change using this idea of the limit of the slope. We'll come back for 2 more examples where we calculate limits of difference quotients. We'll see how they're very similar. Thank you for joining. See you soon.